Welcome. My name is Tony Jimenez. I'm with the National Renewable Energy Lab. I'm going to spend the next hour or so talking about the basics of farm and residential small wind turbines. The slide gives an overview of the topics I'm going to discuss. I'm going to start with giving basically some case studies. I'm going to spend some time talking about wind energy and basically the physics of wind energy, and go from there on how the mechanics of estimating wind turbine energy production. This is something I think a lot of people consider mysterious, but it's pretty straightforward. I'm next going to talk about basically the trade-offs between different turbine designs. There's no perfect turbine. There's only trade-offs between various considerations, and I'll show you how some of those play out. Next, I'll talk about the turbines themselves and how the systems are set up. I'll give a sampling of currently available turbines, and I just want to caveat that just because I mention a particular turbine does not imply NREL's endorsement. And next I'll talk about small wind turbine policy and the various policies that states have enacted to support and encourage the use of small wind turbines. And I'll conclude with some advice and some things to think about when installing a small wind turbine. I'm going to take this one slide to just kind of show the whole wind turbine or wind energy universe. We basically divide the turbines into three categories of relatively arbitrary sizes. The small, they'll be mostly focusing on up to about 10 kilowatts, attached to a specific load, a home, a farm, remote application. At the very large end, you have the large turbines that are used to produce bulk power for the grid. And then in between, you have the intermediate turbines that have kind of the characteristics of both. At the small end, they look a lot like the small wind turbines. They're usually connected to a bigger load. And at the large end, they look a lot like the large wind turbines. This first case study is an off-grid home with a wind PV system. And it makes an important point. If you have an off-grid load, like a cabin or a house or something, it's often best to pair the wind turbine with something else, just PV and or a diesel generator or some sort of fossil fuel generator. That way you'll get much more. Pairing the wind with PV gives you much more consistent day-to-day and seasonal renewable energy production than you'll get from just the wind turbine by itself. This next one is an on-grid home with the wind system. This was installed back in 1999, and I'll emphasize that prices have gone up significantly since then. This is a 10 kilowatt turbine. It was that time California offered very good rebates. I think it still does. That paid for basically half the cost of the system. And given the high electricity prices that were in effect in California back then, this had a very fast payback, much faster than in most small wind turbine systems. Next one is an on-grid farm with a wind. This is with a wind turbine. This is the same wind turbine as before, 10 kilowatts. Produces about 21,000 kilowatt hours a year, so this is in a pretty windy spot. The farmer received some pretty good tax credits when this was installed in the early 1980s. Maintenance them pretty light, and the one instance of damage by lightning was covered by insurance. So this is a wind success story. Next case study is a 10 kilowatt turbine with a senior housing complex in Maine. You can see the combined cost of the equipment and the installation was in excess of $60,000. This is probably unfortunately more typical of what people pay nowadays. That did include a maintenance package, and the town. The big debate in the town was whether or not the wind turbine on a tower was subject to zoning or not. And in this case, they eventually decided it was not subject to zoning. Final case study is a public school in Kansas. They installed a 50 kilowatt turbine on a 100-foot tower. And they're getting about $12,000 a year back from the turbine, about a little over $9,000 in utility bill reduction based on energy that the turbine produces that is used on site, and then additional $2,800 a year from energy they send to the grid, excess energy they send to the grid they don't need. And they're looking at about a 12-year payback, which is, again, is pretty good. I'm going to spend the next 10 minutes or so talking about the wind characteristics and energy potential, and give you kind of an overview of the physics of wind. When we're trying to characterize wind, one of the things we want to know is what are the prevailing wind directions. And this is a wind rose from a site in Montana. It shows that the prevailing winds come from the west and the north. And one thing that's not shown here is you really want to know where the prevailing energy is, which sometimes can be different from the prevailing direction. But in this case, this gives you some sense of where you should install the turbine. If you have some leeway on where to install it on your property, ideally you want to install the turbine upwind of any obstacles, upwind on the prevailing direction. So getting some wind direction information will help you do that. Another concept involved with wind is what we call wind shear. And this is the tendency of the wind speed to change with increasing height above the ground. And in most cases, the higher you go off the ground, the faster the wind speed. And there's some, next slide I'll show a mathematical relationship that describes that. And these differences may look pretty modest, going from, say, 40 to 50 meters, 12.2 to 12.6 meters per second. But as I'll show you later, a very small increase in wind speed leads to a big increase in energy production. This next slide just gives the formula for calculating wind shear. This is commonly used in the United States. If you have wind speed or average wind speed at one height, h1, and you want to calculate it at a different height, say you have data from an anemometer or just off the internet, and you want to scale it to your turbine hub height, this formula tells you how to do it. The exponent alpha is called the wind shear exponent. If the world is perfectly smooth, it would have a value of 0.4, but because the world is bumpy, the typical range is from 0.1 to 0.3. And this alpha, even at the same site, will vary based on time of day, season. So it changes a lot. But for small wind turbines, you're pretty good if you can just talk about kind of an average annual value for alpha. I want to spend a minute talking about the difference between energy and power, because people confuse this a lot, or at least they use sloppy terminology. Energy is a quantity. It's an amount like gallons of water, and it's the ability to do work. And on the electrical side, it's measured in kilowatt hours. Power is energy divided by time, so it's a rate. So the analogy would be gallons per minute. How fast it's filling your bathtub or something like that. A lot of equipment is rated in terms of kilowatts because it needs to be sized to handle the maximum power flows. To go from power to energy, you multiply by time. So, for example, if you had a 100-watt light bulb that burned for 20 hours, it would consume in that time period 2,000 watt-hours or 2 kilowatt-hours. So that's the relationship between energy and power. Remember, one thing from this lecture, the formula is probably the main thing I'd like you to take away from this. If you imagine a straw of wind moving over the landscape, this formula gives the power in that wind. You have the 0.5, which is a constant. The funny shape P is a rho. It's the air density. And there's not much you can do about that. It is what it is. There are modest but noticeable differences. You go from the coast inland up to higher elevations, and in areas where it's cold, the air will be slightly more dense and there'll be slightly more power in there. A is the swept area of the rotor. It's not just the area of the blades themselves, but the whole rotor itself. And basically, that rotor is your energy capture, and so the energy capture is proportional to the size of the rotor. You sometimes see turbines, advertising their sleek, quote unquote, sleek profile. Well, they're basically telling you that they're not going to capture much energy because they made the rotor small. So there's really no point. The V is the important piece. The power is proportional to the cube of the velocity. It means you double the velocity, there's 8 times more power in that straw of wind moving across the landscape. So this cubic relationship is very powerful. You increase the wind speed by 10%, you have a 30% increase in power. Conversely, you decrease the wind speed by 10%, you lose 30. The power goes down by 30%. So it's very, very sensitive to wind speed. This gives the power density classifications. Power density is power divided by the swept area. And we have our 7 wind classes, and this just shows how they're, what power density corresponds to what wind class. The wind speed for a given power will vary a little bit depending on where you're at, again, because of the air density. So if you compare a wind map, say, from a coastal state like Florida, or actually New England, I don't think we have one for Florida, compared to an inland state like Colorado, the wind speeds will actually go up a little bit to achieve the same wind power class, again, because of the reduction in power due to air density. Most utility scale turbines are in class 4 and above. You might see a few dipping down in class 3. Most of the small turbines are in class 1, which is probably not that great, but class 2 or above. Unfortunately, for wind installations, most of the people and most of the loads live in class 1 or in class 2, and the population living in really high wind class areas is pretty small. Next slide shows 3 wind speed distributions. Because of the cubic relationship between wind speed and power, to really have a good idea of the power density, you need not only the average wind speed, but some information about the distribution. And so we often use what's called a Weibull curve. You don't need to know what it is, but it usually has 2 parameters. One parameter that tells you what the average is or what the peak is, and another parameter that tells you how fat or how narrow that distribution is. So if we look at the solid blue line, that's a distribution for an average wind speed of 5 meters per second with a shape factor of 2, which is a common shape factor for inland sites like the continental United States. And you look there, and it has a power density of 146 watts per meter squared. Well, compare that to the dotted blue line, which is the same average wind speed, 5 meters per second, but a different shape factor, a K of 3, which is more commonly for a coastal site. And the same average wind speed, but different distribution, the power density goes down about 30% to 108 watts per meter squared. Finally, let's compare the solid blue line to the solid red line. The solid red line is an average wind speed of 6 meters per second. Again, a K of 2, and a power density of over 250 watts per meter squared. So we had a 20% increase in wind speed from 5 to 6 meters per second, but over 60% increase in power density from about 150 watts per meter squared to 250 watts per meter squared. Again, the very sensitive relationship between power, and thus energy, and average wind speed and wind speed. Next few slides, I'm going to explain how turbine energy production is estimated, at least conceptually. Here's our formula again. The power from a wind turbine is the power in that straw of wind, and we add C sub P, which is just the efficiency factor, which will vary from turbine to turbine, and actually varies even. The same turbine will have a different efficiency depending on the wind speed. There's a theoretical max of 0.59, so there's no turbine that can extract all the energy out of the moving wind. C sub P typically varies between about 0.2 and 0.45 for most wind turbines. And again, the manufacturers try to design their turbines so it has the highest efficiency at the wind speeds that give the most energy. So how do you calculate turbine output? These 5 steps kind of lay it out. You get some wind resource data from wherever you can. Either put up an anemometer or look it up on the wind speed. Ideally, you'd like a full wind speed distribution. And in a lot of cases, you probably just have to settle for an annual average and then assume a K. So usually around 2 is good for an inland site. You will scale the data to your wind turbine hub height. So the data you get is at some reference height, say 20 meters. And you might be thinking about putting your turbine on a 30-meter tower. So you have to scale that data from 20 to 30 meters. So you use this formula here for using the wind shear exponent. Then you multiply the wind speed distribution by the wind turbine power curve. You're basically binning it, and it'll make more sense on the next slide. You adjust for elevation, and then you derate by, I usually knock off about 10% to account for various losses. Turbine unavailability, yaw, blade soiling, the blades get dirty and they're not quite as efficient. You have electrical line losses, just a whole bunch of losses that add up. And so if you knock off about 10% of your gross production estimate, you're less likely to be disappointed. Conceptually, this shows how we calculate wind turbine output. So we have our wind speed distribution, which is this blue dotted line. And so you see it, for example, at 5 meters per second, we can expect the wind to blow at about 5 meters per second, roughly 1,200 hours out of the year. The dotted black line is a wind turbine power curve. The power curve is usually found in the documentation for the wind turbine and shows how much power the turbine produces at various wind speeds. So this one has a cut-in speed of about 4 meters per second and peaks at about 18 meters per second and delivers about 70 kilowatts at its peak. So what we do is we simply divide both these distributions into bins, like shown here, and then multiply the bins by each other. So we multiply the power curve. In this case, it's about a little under 20 kilowatts times the number of hours per year that the wind blows at that speed. In this case, a little under 1,000. And that gives us the total amount of energy produced by winds at that speed over the year, this red thing here. So about 1,500 kilowatt hours per year produced by this bin. Actually, that's tens of kilowatts, so about 15,000. And so all we do is then we just add up the area under this red line to get the total energy production. Some things to note is that the wind speeds that give you the most energy are not the wind speeds that are most frequent, which is here, nor the wind speeds that correspond to the high point of the power curve, which is here, but rather the intermediate ones. And this is very common, especially in areas with modest wind resources, say Class 1, Class 2. The wind speeds that really count, and where the turbine performance counts, is kind of these intermediate wind speeds between about 5 and say 10 or 11 meters per second. So you have a lot of turbines that advertise a really low cut-in speed. We'll start producing power at 3 meters a second, but there's no energy in those winds, so it's not really going to help you. It's how the turbine performs at these intermediate wind speeds that's really going to affect how much energy it produces over the course of the year. This is, if you do this, there's a lot of Excel spreadsheets, so we'll do that calculation for you. This kind of shows you just how it looks in tabular form. So if we look at, say, the bin of 5 meters per second, the wind turbine power curve produces about 6 kilowatts then. The wind speed blows at that speed at about 14% of the year, about 1,200 hours. So we multiply 6 times 1,244 hours and get 7,464 kilowatt hours of energy that is produced by the winds at that wind speed. And so then we just add up all this energy, and for this turbine at this site, you get about just under 92,000 kilowatt hours per year of gross energy production. Talk a little bit about expected wind turbine performance. What are some metrics that are kind of common? We use a term. It's more used for large wind turbines than for small ones, but the same concept applies. Called capacity factor. And what the capacity factor is, it's what the wind turbine produces long term, say over the course of a year, divided by what it would produce over the course of the year if it produced at full rated power. And it makes it easy to plug it in is a shorthand way for showing wind farm production that you can plug into an economic analysis. So for large wind turbines, typically see in the U.S. capacity factors of 25 to 45%. And the reason is that these turbines are placed in the very windiest sites. They're placed on very tall towers, and they're designed to eke out every last kilowatt hour out of the wind. And if the wind resource isn't sufficient to produce enough energy that will in turn produce enough revenue to pay for the project, it just won't get built. Small and medium turbines, you see much lower capacity factors for several reasons. One, they're typically placed in much less windy areas. They're placed where the loads are, your homes, your farms. They're on shorter towers, so they're not as high above the ground. They're designed a little more to high reliability, to minimize maintenance more than to eke out every last kilowatt hour. So they're not quite as efficient. And finally, people put them in for a lot more than just pure economic reasons. And so they're often put in sites that don't have a lot of wind, unfortunately. So you see a fair number of installations where the capacity factor does drop below 10%. So what can you expect from a small wind turbine? Probably 12% is from this example What do you get out of a wind turbine at 12% capacity factor? Well, for a 10 kilowatt rated turbine, 10 kilowatts times 8760 hours per year times 0.12 gives you about 10,500 kilowatt hours per year. And so that's one way to evaluate turbine output. If it's too low, it's probably you're probably better off doing something else. And if it seems really high, you probably need to dig a little deeper. And I'm going to talk a little bit about wind turbine design and the different designs that are out there and the trade-offs involved. I'm going to talk about drag versus lift machines, horizontal axis versus vertical axis, upwind versus downwind, 2 versus 3 blades. Drag machines. A drag machine uses the power of the wind to just push the blade along, just like you would push a door. These are very inefficient designs. They produce very efficiencies. CSPs are rarely get above 0.1, so they're much less efficient than the lift devices. The one exception is water pumping. The old water pumper, from the over 100 years ago, is still being built, and if you have a water pumping application, it's not a bad choice. For generating electricity, avoid drag machines. Their only other benefit is that they're you can build it in your garage if you really want to experiment a little bit. Some features of drag machines are high solidity, and what solidity is how much of the blade swept area is actually covered by blade. Drag machines tend to have very high solidity. And also the tip speed ratio, how fast the tip of the blade moves compared to how fast the wind speed is always less than 1. So those are kind of the two features of a drag machine. The vast majority of machines that are sold now are lift machines. The physics is based on the blades are kind of designed like airplane wings, and the physics is similar to what keeps an airplane up in the air. Characteristics are low solidity, so you just typically have 2 or 3 blades, and much of the swept area is not covered by blade, and that's okay. The other is the tip speed ratio. The tip of the blade actually moves faster than the wind is blowing, and that's a characteristic of a lift machine. Much more energy production out of these than out of a drag machine. Horizontal axis versus vertical axis. So a lot of questions about vertical axis machines. Why aren't they used, et cetera, et cetera. They just haven't had market acceptance. The trade-offs in the package offered by horizontal machines has in most cases proven superior to the overall package offered by a vertical axis turbine. The advantage of a vertical axis turbine is that all the heavy stuff, the gears, the generator is on the ground. But that's a disadvantage of a vertical axis wind turbine, is that it's closer to the ground, lower wind speeds, less energy output. The other piece is that there's they're limited a little bit on size, because you can see in this picture, if for these large vertical axis wind turbines, they need to be guyed from the top, and so those guy wires go way out and they take up a lot of room. So this really prevents you from putting a big vertical axis machine on a tall tower, because then the guy wires would just become too unmanageable. So still a lot of interest. They technically work, but just the horizontal axis machines have gained more market acceptance at this point. Upwind versus downwind. What that refers to is where the blades are with respect to the tower. Most utility machines are mostly upwind machines. For small machines, most of them are still upwind machines, but there's a larger fraction of downwind machines that are becoming available. The advantage of downwind machines is that the blades can be made less stiff, because they'll bend away from the tower. With an upwind machine, you have to make the blades stiff enough so that they don't bend back and hit the tower, which would be a bad thing. A disadvantage of downwind machines is that there's what's called tower shadow. The tower actually reduces the wind speed right behind it, and so there's kind of the blades will feel some stresses as they cross the tower, so you get a little bit more O&M. For small turbines, the upwind machines are a little bit easier to passively yaw. You put a tail back there, it does a really good job of pointing it into the wind. It's a little trickier to do with downwind machines, but it's doable. So you probably want to look at the machine as a whole, rather than just this particular feature when you're making your final decision. 2 blades versus 3 blades. In principle, you could get by with 1 blade and a counterweight, but that's a stupid design for a lot of different reasons. So 2 blades is the minimum you'll see. The advantage of that is you're just paying for 2 blades rather than 3, so it's cheaper and it's a little bit lighter on the hub. The disadvantage of 2 blades is that the forces on the hub are different when the blades are horizontal, when they're sticking out, versus when they're vertical, when they're straight up and down. And so as the rotor spins, there's a cyclic load on the hub and a little bit more wear and tear on your turbine. With a 3-bladed rotor, the rotor is always balanced. The forces are the same regardless of how it's spun. So you'll get less cyclic loading, less wear and tear. So again, it's just kind of whatever the manufacturer prefers. They both work, and it just kind of depends on what's important to you. All right, now I'm actually going to talk about the wind turbines themselves. So if you're still with me, the most math-intensive portion of the presentation is behind you. Small wind turbines are a little bit different than large turbines. The physics is the same, but the regulatory universe and how they're used is they're almost 2 separate universes. On the utility scale side, you're talking 1,000 kilowatts and above. The U.S. are typically installed in wind farms going up to hundreds of megawatts, and they have professional maintenance crews, and they're put in just the very windiest areas. The developer will look for the windiest ridge that has transmission, make a deal with the farmer, plop them in there, and everybody's happy. Small wind turbine is usually associated with a specific load: your home, your farm, your business, your school. It's on the customer side of the meter, so the financial value of the energy is whatever the owner of that load pays for electricity. Typically, that's higher than wholesale rates, which is good because the turbines on a unit basis are more expensive than utility scale turbines. They're designed for high reliability, low maintenance to minimize the need for a maintenance tech to come out and look at it. And they're more designed for low wind speed regimes where the majority of the loads are. You can get some decent amount of production is going as low as 4 meters per second, so about 9 miles an hour. Although at that low, you probably only really makes sense for an off-grid application where you're comparing it against, say, a grid extension. For an on-grid application, I like to see 10 miles an hour, 4.5 meters per second, or 5 meters per second, somewhere in the 10 to 11 mile per hour range before it gets really interesting. Unfortunately, the vast majority of people live in low wind speed areas, and so even the proportion of people that live in areas that are 4.5 or 5 meters per second is at, say, 20 meters above ground is surprisingly small. Small wind turbines, how are they basically designed? Typically have 2 or 3 blades. It'll be aimed into the wind by the tail, so they just passively yaw. The blades are some form of plastic. The way they protect themselves is by furling. So they're designed with springs or your careful hinging that when the winds get too high, the nacelle, which has the rotor, will actually tilt will tilt, and so the rotor will spin out of the wind a little bit, and so that reduces the forces on the rotor, reduces the speed, and keeps the turbine from overspeeding. The generators on most of the small turbines is a permanent magnet alternator. It's direct drive. That means there's one shaft that directly connects the blades with the generator. The permanent magnet alternator is a brushless design, which has some O&M advantages. And typically what comes out of the generator is variable frequency alternating current, or what we call wild AC. After the generator is the controller, it will rectify the AC into DC and use it to charge batteries, or the DC power will go into an inverter that will convert it into constant frequency AC, which you can then connect to the grid. The idea is to produce a simple, rugged design, only a handful of moving parts, and little regular maintenance required. But some maintenance is required, and it's a lot better if the owner is handy than if they're not handy. Towers basically have 2 choices: some sort of guide tower or freestanding tower. The advantage of guide towers is they're a lot cheaper. They need a lot less of a foundation, and you can get guide towers where you can actually tilt down the turbine. Makes it really a lot easier for maintenance rather than climbing up a tower. And if you're afraid of heights like me, it's a really nice thing. If you don't like how guide towers look, some people think they're kind of ugly. You can go with a freestanding tower. Just be prepared to pay a lot more for it. But a lot of people think they look nicer, and it's really up to the buyer. This just shows a one turbine and how it furls. Turbines furl up, they furl to the side. This one kind of furls at an angle. And so going from left to right as the wind speed increases, you can see how the nacelle starts tilting up and away, and that protects the turbine from overspeeding. The controller, I think I've talked about it a lot, mostly talked about it already a little bit. If you have a battery charging application, the controller will control the charging of the load. It will, of charging of the batteries are full and there's no load, it'll divert the energy to a dump load. Most turbines come with some sort of resistor bank where if it's producing energy that can't go anywhere, it'll be dumped, and so it'll keep the turbine properly loaded. If you have a grid connected turbine, you'll have an inverter that connects the turbine to the grid. Most of these are now UL labeled. I think the standard is 1741. And one thing I've noticed is the advertising seems to imply, at least to me, that the whole turbine is UL certified. That is not the case. UL does not certify turbines. They will certify the inverter, and the utility sleeps a lot easier at night if the inverter on your wind turbine is UL listed. On-grid with system without storage. This kind of shows the schematic of the pieces. You have your wind turbine. The controller is kind of part of the wind turbine. Goes to an inverter. The energy produced will first go to meet your load, and any excess energy will go out to the grid. And there's a meter between the inverter and the grid that will keeps track of the energy flows, basically for billing purposes later on. So for how much, so the utility knows how much to credit you for the energy sent to the grid. Maintenance, warranty, and lifetime. These are not, it's low maintenance, not no maintenance. At least an inspection every 6 to 12 months. Laundry list of things to check for. Most of them are like loose connections, corrosion, things like that. Now, as you get into year 10 and beyond, you can expect to make an occasional replace a subcomponent. Warranties are typically up to 5 years now. 5 years is a lot of states mandate a 5-year warranty on equipment to be eligible for their incentives. So the manufacturers have kind of grudgingly gone up to 5 years. And you can get 15 to 30 years with regular maintenance, and I really want to emphasize that. A wind turbine will see as many operating hours in 1 year as an automobile will see in driving 100, 200,000 miles. So think of how much O&M you put into your car driving it that much, and that's what we expect a turbine to do each and every year. So it gives you some idea of what we're asking these turbines to do. Next, I'm going to go through kind of a sampling of currently available small wind turbines, and again, mention does not imply endorsement. One manufacturer is Southwest Wind Power. They're out of Arizona, probably best known for their SkyStream, which was introduced just 2-3 years ago. Designed specifically for the grid-connected market. They basically put all the power electronics in the nacelle, which reduces the installation headaches somewhat. Also pretty well known for their Air X turbines and their Whisper line, which they bought when they bought out another manufacturer. Another manufacturer is Berge Wind Power out of Oklahoma. They offer 2 wind turbines, a 1 kilowatt turbine and a 10 kilowatt turbine. And they've been around a long time. Kind of a newer company is Abundant Renewable Energy, although the guy who owns it has been in the industry a long time. The company offers 2 models, a 2.5 kilowatt turbine and a 10 kilowatt turbine, both for the battery charging and grid-connected markets. Jacobs turbine. This turbine design actually goes back to the 1920s and was a very popular turbine in the 20s and 30s. The intellectual property was picked up by Wind Turbine Industries out of Minnesota, and they've started making them again, and it's a reasonably popular turbine. It has a few more moving, a little more complex than some of the other simple turbines, but still seems to work pretty well. Integrity Wind produces a 50 kilowatt turbine. typically on a lattice tower. Although the case study we saw they used a tubular tower. I believe they have an induction machine, so that means you can connect it pretty much directly to the grid. You don't need as much power conditioning as you do with an alternator. This is a downwind 3-bladed turbine. Final one we'll look at is Northern Power's Northwind 100. It's a 100 kilowatt turbine for the grid connect market. This turbine was designed many years ago for Antarctica, actually. Unfortunately, that made it too expensive to compete in the domestic market. It was just too over designed. So they value engineered it and reintroduced it just about a year ago, and I'm starting to see some installations. So that's kind of a sampling of manufacturers from small to a little bit bigger. Just some other manufacturers, some other dealers. Again, a lot of entrance into the market in the last few years. Policies. I'm going to talk a little, turn our attention to the policy arena a little bit, and just talk about the various incentives that states use to encourage people to install small wind turbines. These are listed kind of in order of usefulness to the wind turbine owner. So most useful are investment incentives or investment tax credits that basically reduce the first cost of buying the turbine. So these usually have a big effect on the economics because they're right up front. Reduce that first cost, and they're pretty popular. If your businesses are eligible for accelerated depreciation, they can depreciate a turbine in 5 years and get the bulk of that in 3 years. So that's if you're a business, that's something to consider. Net metering in general has kind of a modest effect, and its specific effect really depends on the situation. And I'll explain net metering in a little bit. But basically, if you have a very small turbine compared to your load, the production is small compared to your load, all that energy is going to get used into your load. And so net metering really doesn't have much of an effect on the economics. On the other hand, if your turbine is relatively big compared to your load, and you're sending a lot of energy to the grid, but then you're also buying a lot of energy, net metering has a bigger effect on the economics. And I'll get into more into that a little bit later. A lot of states offer tax reductions or exemptions. Some states offer anemometer loan programs. This is not going to do anything for the economics of a project, but it should allow a potential buyer to do a much more precise economic analysis because it's based on on-site data. And the anemometer loan programs often stimulate a lot of interest in small wind. There is as much an outreach program as they are a technical program, at least in my mind. Some emerging policy options are production incentives or feed-in tariffs. These are very popular in Europe, haven't gained much traction in the U.S., although I guess they're being looked at some more. What that is basically the owner of the wind turbine or PV system, for that matter, gets a premium rate for all the energy produced by that system. And usually it's technology specific. And you'll get that rate for a certain number of years. The nice thing about this one to the owner, and I think to society at large, is that it encourages actual production. People who want that incentive are going to want to make sure that their turbine has access to clean wind and is put in an area with a decent wind resource. The other thing that's happening is green tag aggregation and sales for small wind turbines. You can imagine that the wind turbines produce quote-unquote green electrons. We can actually peel off the greenness and sell the greenness separate from the electron, and that's what the green tags are. And big turbines often do it. It's often that the transaction brain damage hasn't worked a lot for small turbines, but there are some programs in place that will try to aggregate a bunch of small wind turbines together and then sell those green tags, and then the owner gets the revenue from the sales of the green tags, so it gives them a little bit of extra money. There's a website there if you want to read more about all the various policies and their effects and all that good stuff. This map just shows residential small wind incentives across the country. A few things stand out. First, a lot of states have some sort of incentive. Second thing to point out is the incentives vary a lot between states. And third thing is there's a lot of variation sometimes even within a state. Sometimes the incentives apply only to the investor-owned utilities, but not to the co-ops. Sometimes a program may just be run by a particular utility. So the take-home message here is you really got to find out what applies to the turbine location. And the Desire USA website shown up top is the best place to go look for those incentives. Next map shows net metering laws by state. You can see that net metering, most states have some sort of net metering legislation. If you see one number, it's the size cap on the installation that's eligible for net metering. If you see two numbers, it's the residential and then the business split. And for three numbers, I don't know. I borrowed the slide from somebody else and didn't ask her what that meant. But you can see a lot of net metering legislation across the country. Sometimes it's monthly. Sometimes it's annual. Annual is more useful to the wind turbine owner, although even monthly net metering is not to be sneered at. And just a lot of variation across the country. In a lot of states, only the investor-owned utilities have to offer net metering, but a majority of the states, net metering applies statewide. I'm talking a little bit more about net metering. If your wind turbine energy can be divided basically into three buckets, and the relative sizes of the buckets depends on the relative amount of energy produced by the turbine compared to the load. The first bucket is energy that is consumed immediately on site. So the turbine's producing energy, you have a load, light, an oven, whatever. The electrons go straight to meeting that load. The middle one, what I call swapped energy, is energy that you don't need at that moment in time, so you send it, so it's sent to the grid. But then at a later time, you need to buy that energy back, and so you buy it back from the grid. And so that's what I'll call that middle one, swapped energy, or energy that's used to offset consumption at another time. If your turbine produces more energy than you use over the true-up period, whether it's a month or a year, than you use, then you'll have what we call net excess energy. And the net excess, always goes to the grid, and in most places, it's either given to the utility or you get avoided cost for it. And very rarely do you get full retail rate for the net excess energy, because the intent behind the net metering is to allow you to size your turbine to meet your load, but not to generate a lot of excess energy. And so the size of these arrows really varies. If your turbine production is small compared to your load, almost all the energy is going to be immediately consumed as it's produced. As your turbine gets bigger or produces more energy relative to your load, you're going to see more and more swapped energy, or energy that goes to the grid, but then you later buy it back. And then once the turbine is producing so much that you've zeroed out your meter and your meter reads negative, over the true-up period, then you'll have net excess energy. And since there's often a mismatch between turbine production and your load, the value of that swapped energy can become an important issue. If your production is roughly equal to your load over the course of a year, probably half the energy has gone to the grid. You've probably swapped half of it. And so whether you get full retail rate for that energy or 2 or 3 cents can make a big difference on the economics. So that's hopefully a not too confusing explanation of net metering. This next slide shows what happens if you don't have net metering, often called net billing, which all it means is the utility is doing the accounting for you. But you have two meters, one that reads what you buy from the utility and the other reads what the utility buys from you. They don't run backwards, so typically the utility is selling at retail rate to you, and you're selling to the utility at wholesale rate. And so that swapped energy is less valuable to you than to the owner than under a net metering situation. Installation. This is I think the last big topic I'm going to cover. I offer you a 12-step program for installing small wind projects. Just kind of in brief, assess your consumption, your cost, your utility tariff. Before you spend money on the turbine, spend some money making yourself more energy efficient. Money spent on energy efficiency will typically pay off much faster than energy spent on either wind or PV. Estimate or measure your wind resource. Typically, for a small system, internet search is all that's really worth doing, or calling your airport or whatever. Only when you're getting to, say, 50 kilowatts or 100 kilowatts or bigger, do you want to start thinking about maybe measuring your wind resource. And it depends a lot on how much uncertainty you're willing to tolerate. Start selecting some candidate turbine sizes and models, and get an idea for what you want to get. Investigate the incentives and the economics. Get zoning approval if you need it. You'll need to complete an interconnection agreement with the utility, and that basically has two parts. One is a technical part that lists the technical requirements of the equipment that you'll be hooking up to the grid, so a lot of safety equipment mostly. And then the other part, tells who pays how much, for the energy that's flowing back and forth. Get your building and electrical permits as needed. Order your turbine and tower, install your turbine, commission the turbine, and then do the O&M so that you live happily ever after. I'm going to talk about some of these in a little more detail. Sources of wind data. This slide gives some sources. There's the source of wind data and information available on the web is much better than even what was available even a couple years ago. So it's really exciting to me. You might be able to get some real data from nearby. And then take seriously the uncertainties in the average wind speed values. Often there's a fair amount of slop there. And remember, those values assume good exposure to the wind. They typically do not apply to the space between your garage and your house. So this is one of my favorite sources. First Look offers a wind map based on an interactive wind map. It's based on Google Maps. So if you use Google Maps, you can do this. Registration is free, and you can go down almost to your backyard and see what wind resource you have. Do note the uncertainty for this particular site. It gives an average wind speed of 4.6 meters per second, plus or minus 0.9 meters per second. So a rather large amount of slop, but at least it gives you a starting point, which is better than people had even 2 or 3 years ago. There are also the wind maps available through the Wind Power in America website, and those are pretty good. It's just sometimes harder to see where you're at. Are you the red pixel or are you the purple pixel? Sometimes it's hard to tell. Micrositing. This graphic hopefully shows graphically what happens downwind of an obstacle. If you have an obstacle of height h, you're going to have a disturbed region that goes about 20 h downwind of that obstacle and extends to a height of about 2 h above the obstacle. So you have the quote there from a turbine manufacturer. Putting a wind turbine on a short tower is like putting a PV panel in the shade. Don't use a short tower just because it's cheapest. Ideally, you want to be outside the turbulent zone. A couple different, one rule of thumb is you want your turbine to be twice as tall as anything around it. Another one, a little more gentle, especially if you have tall trees and whatnot, is you want the bottom of your rotor swept area to be at least 30 feet above anything, within about 300 feet. So do that if at all possible. In some cases, your land may just not support it, but then realize that you're going to take a production hit. And if your turbine is in the turbulent zone, your rotors are in the turbulent zone, you lose twice. The turbulent region is less energetic, so your turbines see less wind, and so they produce less energy. And the turbulent zone is turbulent, so it beats up your turbine more, and so you have higher O&M expenses. So lots of reasons to try to avoid this turbulent area. Obviously, if you own acres and acres of land and it's flat and treeless, then you can going with a shorter tower makes a little more sense because you're not going to see turbulent winds. You'll still get more production if you go higher, but you're not as penalized as somebody who puts their turbines below that are shorter than their trees. Shows an example of a turbine that was put in an area with a lot of ground clutter on a relatively short tower, and it had a very low capacity factor, and this was during the windy season in that area in its initial operation. Now, they probably could have gone with a taller tower, but chose not to. Maybe they had no choice, but just shows that you're not going to get a lot of energy out of a turbine that is not above the ground clutter. Wind turbine sizing. Give you an algorithm for determining kind of the biggest turbine you should be considering for a given load. Typically you don't want your turbine to produce more electricity over the course of the year than your load consumes. Typically it's not going to pay off to do that. First thing to do is determine your annual consumption. So just look at a year's worth of utility bills and add up the consumption data on that. It'll always tell you how many kilowatt hours you used on each bill. Determine your average load. So you divide your annual consumption by 8760 hours per year. Then all you do is you divide your average load by a guesstimated capacity factor. For most people, it's probably just 0.1. If it's the site's in a really windy area, high class 2, class 3, you may use 0.2. Exact number is not that important. It's just to give you kind of a starting point. You do that division, and that'll give you approximately the largest size turbine you should consider. You can then select a turbine around that size range because you're probably not going to find one that exactly matches. Go through and calculate its annual energy production, and then repeat for any of the turbines that you may want to consider. And at that point, some other considerations may lead you to go with a larger or smaller turbine. The larger turbines tend to be a little bit cheaper per unit size than the smaller ones, so it may be you may be economically beneficial to go with a slightly larger turbine as opposed to a slightly smaller turbine. On the other hand, if you don't have net metering and there's a big mismatch between your load and the turbine production, you may just want to go with a smaller turbine. Or you just may not have $50,000 lying around, and you just go for a smaller turbine to reduce the first cost. But at least you have some idea of where you're starting from if you follow this methodology. Frequently asked questions on sighting. Not too many issues with radio and TV interference because the blades are wood or fiberglass, so they're transparent to the radio waves. Noise can be an issue depending on the turbine, and it's probably a bigger issue with small turbines than with large turbines. The smaller turbines have higher RPMs, and so they're actually a little bit noisier than the larger turbines. And so ideally, you go out and check, and if you can find an installation of a model you're considering, you can listen to it. You may not want to put it right outside your bedroom window, and there are some noise test reports on the web for some turbines at that website. Single turbines have very little impact on birds, and unless you just see birds seasonally flying right over your house, you put up a wind turbine and you probably won't kill any birds. You might kill one or two over the lifetime of the turbine. FAA, most turbines fall below the 200-foot height limit that the FAA really cares about. So unless you're really close to an airport, you probably don't have to worry about the FAA. Weather, lightning. Lightning is a good reason to properly ground your turbine and do all the lightning protection stuff that the manufacturer recommends, and that will reduce the chances of lightning frying your wind turbine. Remember, if you install it right, it's the highest thing in the area, so you do want to ground it properly. Severe storms may be a problem, maybe not. Survival speeds are typically above 100 miles an hour. But if it takes a direct hit from a hurricane or a tornado, you're probably going to be damaged. Hail damage hasn't been much. We haven't heard of any issues with hail damage. Ice shedding. I actually heard just a couple weeks ago about an instance where a turbine threw a piece of ice a fair distance, but very, very, very rare. The ice buildup typically destroys the aerodynamics of the blade, and so it just won't spin, and then the ice will just kind of melt and fall straight down. So a vanishingly small problem. Questions to ask about a turbine you're considering, especially if it's relatively new. What's the performance? You should get a power curve. A lot of manufacturers have a little table saying if your hub height wind speed is 5 meters per second, you can expect X kilowatt hours per year per month. So there should be something that indicates the energy production. Was it a performance measure in a field test? You're probably not going to be answered this question, but in the old days, a common way to get the power curve was a manufacturer would put the turbine on a stub tower, and a guy would hold it in the back of a pickup truck. And the pickup truck would drive at various speeds, and they'd measure the power output. That's really not a good way to do it, and so they're going more towards real field testing. Has the performance been independently verified? For most small turbines, the answer is no. You'll have just basically what people say after they've been installed. There is in North America, the industry is trying to form a small turbine certification body. They will kind of give it stamp of approval for turbines after they've been properly tested, but that's still very much a work in progress. Is the turbine labeled for compliance with UL 1741? This is becoming kind of a minimum requirement to be able to connect to the grid, and most turbines have UL compliant inverters. And again, the inverter is UL compliant, not the whole turbine. The advertising sometimes tries to fuzz that issue up a little bit. Is it compliant with an IEC design safety standard? There is an IEC, and that stands for International Electrotechnical Commission, and they have a small wind standard that almost no small wind turbine has been tested to because it's too expensive. So they're trying to develop a standard that the manufacturers can live with. And again, that's a work in progress right now. Who provides your parts and service and your warranty service? The Chinese manufacturers that'll drop ship a turbine to your door, but then who provides the O&M? Who does the installation? And has it been demonstrated? Do you really want serial number 2? In most cases, the answer is no. And so, it's been installed somewhere else. Can you get some information about it? So these are the questions to ask. Kind of for any other consumer device. Buyer beware. Ask questions. Do your homework. Just a sample from a spec sheet. It has a power curve. It's about 4 square inches right at the bottom corner, but it's there. And it has a table that basically shows the results of all the math. So in this case, if you have an average hub height wind speed of 5 meters per second, you can expect about 155 kilowatt hours a year from the turbine. At least the ones I've spot checked, they're pretty consistent between the table and the power curve. The one thing you got to remember on the table is that tends to be gross production, and you probably want to knock off about 10% to get a better estimate of what you'll actually get out of the turbine. But you want to see something like this on the manufacturer's spec sheet. If you don't see it, be suspicious. Economics. What's the cost of installing it? You have an all-in cost. I've looked at a lot of these, anywhere between about $4,000 and $10,000 per rated kilowatt. This includes the turbine, the tower, the civil works, and the installation. So, for example, your total out-of-pocket costs for a 3 kilowatt turbine are going to be anywhere between $12,000 and $30,000, and a lot depends on the tower height and things of that nature. If you're really handy and you want to do some of the civil works yourself, you can save some money on this upfront cost. O&M is really hard to capture, and there's not a lot of good information. But I would say the manufacturer will say a penny a kilowatt hour. I'd say you probably really want to plan closer to 2. You shouldn't hopefully pay very much up front during the warranty period, but just kind of put that money to the side, and as you get in the out years, it'll average out. You'll have to start paying some bigger money to do occasional replacements. And again, the more O&M and inspections the owner can do, the lower the out-of-pocket O&M expenses. Some questions to ask during the economic analysis. Is the production estimate reasonable? Are you properly accounting for the financial value of the energy produced by the turbine? In the case, if you have a demand charge to your bill, the value of the energy produced is really the kilowatt hour piece. It says you pay X number of cents per kilowatt hour. That's really the financial value of the turbine energy. A turbine will generally not have much effect on the demand piece of your bill, so you want to watch out for that. What proportion of the electricity will go to the grid? If you don't have net metering, that becomes a moderately important question to ask yourself, because the financial value of this energy depends on whether you got net metering and then the buyback rate that the utility offers. Properly considering state and local incentives, and are you accounting for O&M? Finally, to wrap up, I'll just have a couple slides with some sources of additional information. Well, first, I guess I'll review what I talked about. This is what I talked about. Kind of showed you some case studies. I talked about the physics of wind, and particularly the cubic relationship between wind speed and wind power. Went over how turbine energy production is estimated. Went over the trade-offs between different turbine designs. I reviewed kind of the turbine technology and how it works. Gave a sampling of currently available turbines. Again, mentioned does not mean endorsement. discuss the various policies that are in place to support the small turbine industry and encourage installations, some practical considerations regarding installation, and we've reached the wrap-up. A good place for additional information is Paul Geip's book, Wind Power, the one on the left. I think it's like 300 or 400 pages, but it goes into very many aspects of wind energy. And if you're considering a wind turbine, this book will pay for itself many times over if you read and study it. If 400 pages is a little too much to dive into, he wrote a kind of a shorter book called Wind Energy Basics, and you could check that one out as well. Next is a laundry list of websites. The AWEA website. AWEA is the American Wind Energy Association. It's the U.S. Wind Industry Trade Group. They have a small wind section. Their Ask an Expert section is very well done. That's done by Mick Sagrillo. He's not government, so if he sees something he doesn't like, he just fires with both barrels. It's really blunt, good reading. The WPA, Wind Power in America website, it also has a small wind section. We offer links to our small wind consumer guides. We have a U.S. one, and then we have state-specific ones you can download for a lot of the states. And there's also you can download a small wind economic model, so you can do your own performance and economic modeling. It's just a little spreadsheet you can download. Home Power is a really good website. They're a magazine. It really gets into the nuts and bolts of renewable energy installations. They focus more on PV, but each issue typically has at least one wind case study, and they offer some of their best stuff available for download online. So the Wind Turbine Buyer's Guide is a good read. And finally, the manufacturers' websites. A lot of them offer a lot of useful information. So with that, Carpe Ventum, seize the wind, and I'll leave you with this one last case study showing a small wind turbine that was installed at the home of George Bush Sr. And at this point, if this was live, I'd be taking questions. But if not, since you're just listening to this recording, good luck. And if you install a wind turbine, I hope this has proven helpful to you.